Good afternoon, everyone. It is really a very good honor to be here to do a presentation, and thank you very much for Professor Yao to give me this chance. Actually, Professor Ho mentioned this morning about how he trained your PhD students. As the third generation of the Professor Ho's academic family, actually this is what I experienced during my PhD study under Professor Lu Haley's guidance and my postdoctoral study under Professor Cheng's guidance. Actually, I think during my study under their supervision, the most exciting thing and also the most and also the most stressful thing is that to meet them every week. So each time when I think, oh, tomorrow is a day to meet with them, I always feel a little bit nervous, and I don't know what kind of situation I will face with. But actually, at the initial stage, I always felt very disappointed because they ask many challenging questions, but I cannot answer. But gradually, as I meet them many times and know many things from them, I think I gradually know how to do the right way to do a research. They teach me how to ask the right questions and doing the research. So I think that today Professor Ho also mentioned about ask the right question is very important. Not only in research but also in our lives. So I'm now became a new academic in Shanghai University. There is still a long way to go, but I think I will learn from Professor Ho, my supervisors, Professor Li, Professor Chen, and all the scholars here, and to know how to ask right questions in my research and life, and also enjoy my life. Okay. So I'm the last speaker. I will try to finish it before 6. Okay. So the topic of my today's presentation is about a simulation budget allocation procedure for enhancing the efficiency of optimal subset selection. This is a joint work with Professor Jie Xu and my supervisors Lu Heili, E.K. Peng, and Chen Hongchen. So this is the outline of my today's presentation. So firstly, let's go to the introduction part. Actually, in real industry, there are many kinds of optimization problems. For this kind of problems, we want to find the optimal solution under certain feasibility region to maximize or minimize certain objectives. But for this kind of problems, usually we have some difficulties, especially when the systems are very complex. The first one is that how do we do the evaluation? So as the systems are very complex, sometimes nowadays we usually using the simulation to do the evaluation to help us to handle the complexity of the systems. The other question is about how to find the best. There are already some optimization approaches developed to answer these questions, but under the simulation scenario, because of the black box characteristics and other characteristics, some traditional optimization approach cannot be applied. Therefore, many researchers do some researches on developing the approaches that want to solve the optimization problem with whose the objectives are evaluated by simulation. So this is the simulation optimization approaches. This is a general formula for the simulation optimization approach. Actually, for this kind of problems, just as Professor Chen mentioned, one challenging question is that usually when we do the estimation of the estimation of the performance of each solution, we need to run many replications to get a sample mean to estimate the performance of it. The another challenge question is that the solution space for the complex optimization problems may be very large. So under these two kinds of challenges, solving the simulation optimization may be very time consuming. In this kind of situation, we need to consider the computing efficiency problem for the simulation optimization. Therefore, the optimal computing budget allocation approach proposed by Professor Chen is exactly to answer these kind of questions. So, but in many situations, we think selecting the best designs is not enough. Many of the current or the OCBA research works are only considered to selecting the only one best. But however, we may meet with some situations that we need to select the optimal subset. That means not only just one. Not owning one best designs. For example, for the decision makers, when they want to do the decision making, they need to consider some qualitative criteria or also some political things. So they want the decision support system only provide them some good designs. Based on that, the good designs, they can consider to make the decision by themselves. So another example is that when the problem is very complex, usually some in industry, they're using the low fidelity model to do the evaluation as a screen of many kind of solutions. And based on the low fidelity evaluation, they select some good designs. And then they do the high fidelity evaluation to select the best from this one. So under this kind of situation, we also need to select the optimal subset. Actually, during my PhD study, I doing an internship on a simulation optimization consultant firm. That firm actually they provide a consultant to the airlines. They want to they have one simulation software named as DSimSpell. They provide the optimal inventory policy to their customers to such that the cost can be minimized. So especially they are applied for the airlines companies. So you see. For the one plan, there are many numbers. There are many kinds of spare parts. They need to determine the inventory policy for each spare part. Under this kind of situation, we know actually the solution space are very huge. And the another situation is that when for one configuration of all the inventory policy, when they doing it as input into a simulation software, actually it usually took about 1 or 2 hours to run one simulation. So how do they figure out this kind of very time-consuming problem? The way they did it is that they use a low-fidelity simulation evaluation, and they select the optimal subset from them, and then use a high-fidelity simulation model to solve it problem. So the third kind of example is that for some population-based approaches, usually they need to select an elite subset, then to determine the search direction. So this is some kind of examples about doing the optimal subset selection. So for the literature review part, I think Professor Chen and Xiyang already gave many literature review about the OCBA and also the simulation optimization part. So I just skip them. Then we go to the problem formulation part. So our problem is that we totally have k alternatives, and we want to select the top m from them. And we have the total computing budget T. So based on the OCBA framework, this is our problem, the way to model it. So to solve this problem, actually, we need to answer 2 questions. The first question is that, how do we formulate the PCS? The other question is that, how to get the optimal allocation rule? So let's go to the first question, how to formulate PCS. So what is the probability of character selection? I think just now Xiang also mentioned the definition about character selection. So under the subset selection problem, suppose we have k alternatives and the optimal subset is from 1 to m. So actually the one character selection means that all the sample means for this optimal subset should be less than the sample means of other sample designs. So this is our PCS. However, under the current framework, the PCS don't have the closed form expression. So we using the lower bound named as approximated probability of character selection to approximate it. Then how do we do the approximation? The way we see, actually, this is optimal subset. This is all the other designs. So the boundaries, we can see, actually, these two boundaries are the keys to determine which designs are in the optimal subset. Therefore, we use the design m and design m plus 1 as the threshold to derive our lower bounds. So this is the expression of we using the xm, the m design as a threshold. This is a lower bound we derive. And also we can use the sample mean of a design m plus 1 as the threshold to build the lower bounds. So the APCS M, the approximated probability of character selection we used in this paper is that we want to select the best one from them as the APCS. Okay. So this is a way we answer the question about how to formulate PCS. Then we go to the next question. It's about how do we derive the allocation rule. So for this kind of OCBA model, actually APCSM is the maximum one of APCS1 and APCS2. So this can be separated into two optimization problems. We can prove that these two problems are convex problems. Therefore, we can apply KKT conditions to derive the optimal rule for this kind of problems. These are the optimal rule we derived. Actually, these are very similar to the OCBA rule. The difference is that we can see this part. We can see this part. And the difference is that for the design M and M plus 1 means they are the boundaries of the optimal subset. They follow the square root rule, means they can have more replications because they are the key issues to determine whether a solution should be in the optimal subset or not. For the other designs, they follow to a noise to signal ratio. This means if the designs are far away from this boundary, they need less replications. And on the other hand, if the solutions actually have high variance, it should get more replications. So this is the basic insights of this allocation rule. So we choose the one can give us more APCS as our OCBA M plus rule. Based on this rule, actually, if we put the M equals to 1, means the best design selection problem, the allocation rule we derived actually is reduced to the OCBA1 allocation rule, which is proposed by Professor Chen. Okay, so this is our allocation rule about the optimal subset selection we proposed in this work. So the third part is about asymptotic convergence rate analysis. Why we did it is because that each time when we derive an allocation rule, how do we evaluate the goodness of one allocation rule? One way is that way to do the numerical experiment. So is there any theoretical framework for us to do this kind of evaluation? So just now Xiang mentioned about the large deviation theory. So in this work, we're also using the large deviation theory. We consider the convergence rate of PIS goes to 0 as a measure to determine whether a allocation rule is good or not. Okay. So this is a formulation of probability of incorrect selection. Very lucky thing is that we can have this upper bound and a lower bound and upper bound. They have this common element. So if we take a log and under the t goes to infinity issue, we can get actually the probability of incorrect selection is convergence rate can have this kind of formula. This formula actually the GIJ means the convergence rate of one event of incorrect selection. So we choose the one has the lowest convergence rate as the is the convergence rate of the PIS, because the slowest one determines the overall things. Okay, so this is a convergence rate derived based on the large deviation theory. Under the normal distribution assumption, we can get the theoretical formula of the OCBAM proposed in 2008 and the OCBAM plus algorithm proposed in this paper. And we also did some derivative work to prove that under some conditions or situations, our OCBAM procedure is actually can get the highest convergence rate compared with optimal subset selection algorithms. Okay, so this is a convergence rate analysis part. So the numerical experiment part, I just show only one case it's about a basic experiment. Suppose we have in total have 50 designs, and we want to select the top 5 from them. So under this kind of situation, we can see this figure shows the efficiency of the work we proposed OCBAM plus, and we compared it with equal allocation and OCBAM. We can see actually under the same computing budget, our algorithm can get the highest PCS. Okay, so another thing is that when we want to show the theoretical convergence rate, based on that kind of measure, we can also find that our procedure can get the highest convergence rate with compared algorithms. Okay, so put in summary, actually in this kind of work, we derived an allocation rule named as OCBAM plus for the optimal subset selection problem. So this algorithm, it can reduce to the OCBA1 rule proposed by Professor Chen, and also based on the convergence rate analysis, we can prove that it can have the very high convergence rate. So this is a basic the basic works about this kind of things. Besides this, I also did some research works about the OCBA integration with some searching algorithms to solve the large-scale optimization problems. And now I also did, do many research works under Professor Chen about the ordinal transformation on the models, that part. Yeah. Okay, so this is the end of my presentation. Thank you all.
Thanks for ending before the dinner. Thank you. Okay, so any comments? Okay. Okay, good. So we can have, okay, so if no questions, we can finish the session in the afternoon. And thanks for everyone coming.